Hello students, welcome to JCE Connect series of lectures. So in previous lectures we have solved uh, some numerical problems on Pelton wheel where we have calculated work done by the jet and efficiency of the jet. In this particular session, so I'll be solving a problem that is a design of a Pelton wheel, how to design a Pelton wheel and working proportions of a Pelton wheel. So let us first discuss about the design procedure of a Pelton wheel. So what do you mean by design of a Pelton wheel? Here the design of Pelton wheel means, the following data is to be determined. So here the design means not we're completely designing the buckets or the completely designing the uh, runner of a Pelton wheel. Uh, so just we are calculating here the working proportions of a Pelton wheel. So in this particular uh, uh, design, so the design means we need to calculate the diameter of the jet, then we need to calculate the diameter of the wheel, then the width of the bucket, so which is to be generally taken, it is the value is between 3 times of diameter of jet to 5 times of diameter of jet. So I am taking here as 4 times of diameter of jet. Then you have to calculate the depth of the bucket, which is to be taken 1.2 times of diameter of jet, and number of buckets on the wheel. The number of bucket on a wheel means this is the wheel, how many number of buckets to be optimum number of buckets we need to calculate optimum number of buckets. So the jet, whatever it is striking, it should not miss by striking the bucket. Okay, then size of the bucket means the width and depth of buckets are to be calculated. Okay, so all the dimensions are being proportioning uh, by using the diameter of jet here. Okay, so this is a design of a Pelton wheel. Then design procedure. So if you look at the design procedure, so in design procedure the power will be given, the how much power Pelton wheel to be designed, or how much power needs to be developed by the Pelton wheel, and the RPM also given. For the given power and for the given RPM, you need to design the Pelton wheel. So design a Pelton wheel means, as I discussed previously, so that parameter needs to be calculated. So in this particular design procedure, the design of a Pelton wheel turbine to develop a known power P running at n RPM with an overall efficiency of eta O, the following procedure is adopted. It means the power will be given, RPM, that is RPM of that wheel will be given, then the how much efficiency it needs to generate, that is overall efficiency. Then for that you need to calculate what the diameter of jet should be required, or how many number of jets are required to develop a particular power, or what diameter of wheel is required, and how many number of that is optimum number of buckets are required to generate the given power. So for that, so as we know the overall efficiency formula, so that is the first step we need to calculate, find the rate of flow through the turbine. So since the overall efficiency will be given, the shaft power, the known overall efficiency and the known shaft power, then we can easily get the how much discharge is passing through the turbine. So overall efficiency, as we know, it is the ratio between the shaft power and the water power. So shaft power is a P, then the water power is rho into G into H into Q. So in this, the P is given and the head will be given, then you need to calculate how much discharge is passing through the turbine, that is Q. So that is eta O, that is P divided by rho G into Q into H. So from this you can easily get the value of Q. So this gives you the discharge through the turbine, total discharge. Then from a known head H is given, compute the jet velocity. So as we know the formula for calculation of actual velocity, that is V equal to CV into root of 2gh. Since h is given here and CV will be given, if not given, CV to be assumed between 0.97 to 0.99, and bucket velocity as that is a U, or you can call it as a wheel velocity, that can be easily calculated, that Ku times of root of 2gh. So here this root 2gh, u equal to Ku into, actually this is theoretical velocity. As you know, the Ku is the speed ratio. The speed ratio is what? It is the ratio between the wheel velocity and the jet velocity. Wheel velocity and the jet velocity. From the speed ratio, we can easily get the wheel velocity or the bucket velocity, that is u equal to Ku into root of 2gh. And this Ku to be assumed or between 0.462, as we know the value of Ku is generally lying between 0.43 to 0.47 or 0.48, and theoretically its value is 0.5, but that 0.5 is not actually possible. Some practical problems, so we need to take between 0.43 to 0.47. So once we calculate the velocity of the bucket or velocity of the wheel, the next we need to calculate, so what is the pitch circle diameter or diameter of wheel. So that diameter of the wheel, the for wheel diameter, it is also called as a pitch circle diameter. So as we know the formula u equal to pi dn by 60, this is a rotational velocity. The rotational velocity u equal to pi dn by 60. Since n is known and u is known, you can easily get the diameter of wheel, that is d equal to 60 into u divided by pi n. Then after calculating the diameter of the wheel, calculate the diap jet. The diap jet to be calculated by using the formula, that is a ratio between, this is a ratio between pitch circle diameter to jet ratio. So as we know the jet ratio will be d by d, that is a diap wheel divided by diap jet gives you the jet ratio. From this we can easily get the diameter of jet. If we know the this jet ratio, generally for a maximum maximum efficiency, this ratio will be between 11 to 14. Then after this one, fifth step, obtain the total jet area. The total jet area can be given as A equal to Q, because we know the total discharge divided by the velocity. This is the total area of jet. Then also you can easily get, once you get the total area of the jet, if number of jets are n number of jets are provided, then area of single jet can be calculated A equal to pi by 4 into d square. Okay, A equal to pi by 4 into d square. This is the total area of jet. This is area of single jet. Okay, then find the number of jets. Then calculate the number of buckets required, optimum number of buckets on the wheel. That can be calculated by using the formula z equal to 0.5 times the jet ratio plus 50, where m is d by d, diap wheel divided by diap jet. So after calculating the number of buckets, then you have to find the dimensions of the bucket. The dimensions of bucket means, as we know that this is the shape of the bucket. This is the shape of the bucket. So we need to calculate what is the width of the bucket, what is the groove size, then what is the radial length, then the depth of the bucket. So how much to be taken, this B, L or C, as I discussed previously. So you have to express these things in terms of diameter of jet. I hope you understood this one. This is what we call as a design of a Pelton wheel. Okay. So next we'll take one numerical problem and we'll try to understand whatever the procedure we have been discussed so far. So you can easily understand the procedure what I have discussed if we solve one numerical problem. Okay. So try to uh, understand this design procedure. This is the design of Pelton wheel is very important for the examination point of view. Many a times the question will be asked in a question video question paper. So generally it is been asked for 12 to 15 marks. Sometimes for 20 marks also it is been asked. Design a Pelton wheel for the given data. So like that the question will be asked. So we'll see how to design a Pelton wheel. Okay, so we'll see in the next class. Okay, thank you.